F08 is about transactional memory, and the key idea with transactional memory is to let the programmer focus on algorithm and implementation efficiency and not worry too much on data races and synchronization between different threads. And this is done by letting the programmer create transactions, and then the different threads perform these transactions occasionally. I mean, they do not only do transactions, but sometimes they enter a transaction. And if two threads happen to modify the same data, then at least one of the transactions is restarted. And if the transactions are restarted too many times, it will make the program slower. But that's it. So the programmer has to think about restarted transactions for performance, but not for correctness. Okay, and we will look at both hardware and software implemented transactional memory. We will see that the hardware transactional memory is the only reasonable way to use it for C and C++, for instance. And we will look at the performance numbers from 3 IBM machines and 1 Intel machine. For functional programming languages, such as Clojure, it is more reasonable to do it in software, entirely in software. Okay, and we will see why this is the case for them. But before going further, we will look at a simple example, namely a simulation of a popular Swedish bank app called Swish, which what we can do is to transfer money between bank accounts using phone numbers. I mean, yeah, we send money to a mobile phone number. Okay, so what this does is it's a very trivial simulation of this, but we have bank accounts with a balance, and no phone numbers are involved, just the index to this array of accounts, and each gets a start balance, and then we do all the work here and simply randomize accounts and amount, and swish this to between these accounts. Okay, I mean, we transfer it from the from account to the to account and this amount, but only if there is a sufficient fund. Okay. If you think of a situation where there are, I don't know how many concurrent swish transfers there are per minute, for instance, in Sweden, but it's a really huge number, is my guess. Okay, so what is the risk that the balance is modified at the same time, so that there would be a data race? I would say it's quite small, except if, for instance, at a restaurant, many people decide to swish to somebody, for instance. Then, well, that's an example. But in general, it's really very low probability that there is a data race. So why not just speculate and run this in parallel and hope for the best? It doesn't work like that because we don't want to have a probability that there is a bug. Okay, but if we let either the software or hardware detect the data race and restart this function when there was a data race, then it may be much faster than every time having to lock the accounts. Since almost all of the time using a lock, it is completely unnecessary. I mean, it's just wasted clock cycles. Okay, so how can we do that then? Well, a transaction, it's a sequence of reads and writes. The transaction obviously contains other instructions as well. It's a part of the code. But it's the reads and writes that are checked. Okay, so the idea is really to take a chance without locks, and if there are conflicting accesses between two different transactions made by different threads, then at least one of the transactions is started again. I mean, read on. Okay, so what the programmer has to do is to identify the start and end of a transaction. That may sound trivial, but in fact it's not, because if we make two big transactions, then the probability that there are conflicts and restarts obviously increases. And if we make two smaller transactions, then some overhead of processing the transactions, I mean committing the data, there is some overhead involved. It will outweigh the benefit. So although it is a nice feature, it's not the perfect way to make super efficient, simple parallel programs. But this is a really interesting approach.